Okay, thanks everyone for joining another CB talk. Today we have Fabio Pizzati. He's a second-year PhD student at INRIA Paris. His research interests lie in the intersection of computer graphics, generative networks, and physics. So he's going to talk about physics-informed image translation with GANs, mainly covering his recent two papers, CVPR 2021, CoMoGAN, and his previous work, ECCV 2020. So as usual, feel free to ask questions in the middle of talk. Thanks again, Fabio, for accepting my invitation. Yours. You can start.
Okay. So again, thank you for inviting me and for the nice introduction. As it has been told, my name is Fabio Pizzati, and I'm a PhD student in the INRIA Paris group. I'm supervised by Raoul de Charette, and today I'm going to present to you, our latest results in terms of physics-informed image translation with generative adversarial networks. So the talk is going to be focused mainly on image-to-image translation, which is a particular kind of task which is typically accomplished by using GANs. So the idea is to take some kind of source images, for example, this one in the synthetic domain, so in the source domain, and to apply to them a different style in order to modify their appearance. For example, in this case, we learn a realistic style from a target domain, which is indeed real, so from target images in a unsupervised fashion, and we are able to modify the appearance of the image without modifying the scene context. So the scene represented is actually the same. Of course, there are many other transformations possible. For example, here we map from a clear weather scenario to an adverse weather one, so adding snow inside the image. Of course, this has been pretty well discussed recently. They have many applications, for example, in computer graphics or in domain adaptation, because it makes possible to reuse this kind of images in different scenarios, so we can also reuse annotations. It's pretty great, but what we noticed in our recent experiments is that they may have some failures mode, or they may have insufficient performances in some cases. For example, I'm just going to make a little spoiler of our investigation on this topic. This is an image-to-image translation network which is trained to translate from a clear weather scenario to a rainy one. And as you can see, the results are not as good as the previous one. So there is a very evident artifact here. So the realism of the image is highly impacted by this. Our idea is that this system may benefit from the underlying knowledge of the physics of the transformation that we are trying to approximate. For example, what you can hypothesize, for example, is to inject some kind of a physics guidance in our image-to-image translation training in order to improve either the network performances in terms of realism or the network capabilities. And in this case, we get to a physics-informed image-to-image translation. So at this point, you may have some questions about this. For example, which kind of physics guidance am I talking about, and what we can actually do with this kind of guidance? So when I talk about physics guidance, I mainly talk about the physical models of the transformation. And since we are talking about computer visions, they are mainly applied to images. And what we can do with these models during training is dependent also on the realism and how the model approximates the physical phenomenon. For example, a first investigation axis relates to naive models. Let's think about a physical phenomenon which you all know, which is night. So a transformation from day to night is very difficult to model from a physical point of view. But we can think about night as a darker day version. So we can use a very simple physical model which just takes some input data in image and just darkers, like reduce the brightness inside them in order to model somehow night. Even if these kind of models are highly unrealistic, we are able to use them in CoMoGAN indeed in order to regularize and organize a target manifold for achieving a continuous nonlinear translation. And this one has been accepted at CVPR. Again, there are some kind instead of physical phenomenon which are pretty well known and well studied in literature. One of them that we investigated is raindrops. So for raindrops, we have really realistic models because a raindrop is kind of simple to understand. It's just some water on a lens and it has some refraction due to the incoming light. So we're able to render them in a very realistic manner. And if we have a realistic physical model, what we may want to do is to take advantage of the realism of the physical model in order to compensate some of the lacks of the image-to-image translation network. And this is related to the other work, the ECCV one that I'm going to present later. So mainly the presentation is going to be focused on CoMoGAN. So we are going to discuss for most of the time that one, but at the end I'm going to explain as well the technique behind the ECCV work. So let's maybe start with CoMoGAN. All that I'm saying is of course already available on archive, but if you want also to have a look at the code and the actual implementation, we provide an official version on GitHub. So if you want to have a look at the losses, the network architecture and so on, everything is public. Okay, so I talked before about image-to-image translation, and I talked about the simplest case of image-to-image translation, in which we have one single source domain and one target, and we are interested in mapping from source to target, as I showed you before, from synthetic to real. There are more complex systems which perform multi-target image-to-image translation, in which we have one source domain and multiple target domains. And a typical case of this is, for example, with face mapping. We can have a generic male face here, and we can hypothesize to map to different target domains, which are females with different hair colors. Of course, this requires additional supervisions on a domain point of view. So we have to distinguish between different classes of female at the reorganization of the dataset. What we do in this work is to depart from this state of the art and to let's say create a new task for image-to-image translation, which we called continuous image-to-image translation. So in continuous I2I, what we assume to have is a single source domain, as in the other cases, but what we have as a target domain is a mixed set of heterogeneous and unordered, let's say, smaller target domains. So as you can see here, we have no distinctions between the different target domains. What we want to get is first a reorganization of the target domain. So we have to make some sense of the possible images that we have in the target domain. And we want to also be able to translate in every point on this possible path that we are tracing between target domains. So the idea is to learn a manifold in which the transformation makes sense, not only in terms of target domains, but in terms of the all continuous transformation. I know that this can be kind of abstract, so I'm going to give you a practical example of how this system could be used. For example, let's suppose that we have as source images some daytime scenario. So we have this kind of images as source data set. And as target, instead, we have a mixed heterogeneous set composed by nighttime images, dusk, sunset images, which is very varied, and everything is mixed. So we have no distinction inside the target dataset on which images are nighttime, which images are sunset, and so on. The idea is to perform a continuous transformation, for example, from day to night by passing through the intermediate condition in a nonlinear manner. So in other words, what we are trying to do is to extrapolate a manifold in which it's logical to perform the transformation. And in particular, we can identify different types of manifold, which we also did in this work. So for example, given the example, so a day to night example that I gave you before, we can identify a continuous linear manifold. So to perform a continuous linear image-to-image translation in which we pass from day to night by passing through a sunset condition in a linear manner. So the idea of this is that we also have a parameter here, which is very important for the presentation, which we call phi, that symbolizes the absolute positioning inside our manifold. So the idea is that we take some source image, and if we increase the phi, then we move along the sunset, and if we increase again the phi, we move along the night. Okay. Looking at the physical phenomenon that we are trying to approximate in this paper, it's also true that it's not always like this. So we can hypothesize novel and more complex manifold shapes. For example, a cyclic manifold in which the transformation from day to night passes through an intermediate dusk condition. But if we want to pass from night to day, then we have to pass through another condition which is different from dusk, which is simply what we are experiencing every day. So it is dawn. The idea here is that we can define the manifold in which we are organizing the data on, and in this case, we get a continuous cyclic image-to-image translation that in this case, we call day-to-time-lapse, because we are able to map from any point in day to any point in the time-lapse that we have as a target domain. So that's the main idea of what the network should be able to do. Now, since we don't have any annotation of the target dataset, and again, everything is mixed, the network has to be provided with some kind of supervision in order to reorganize the target data. And how we plan to do that? We plan to do that with the physical models that I introduced you before. So the idea is to get some physics-inspired model guidance in order to get the manifold reorganization while we get the realism on the real data. Again, I'm really talking about naive models, so I'm just going to give you a perspective on how naive are these models. This is just a random perspective of all the models that we use in the papers for different experiments. So on the first row, you can see the input images, and on the second row, you can see the model outputs for different model characteristics. For example, this is supposed to be a time-lapse model. So this is supposed to be a model which is able to generate intermediate dusk, dawn, and night conditions. So as you can see, the model that we are using for guidance in this experiment is just lowering the brightness and applying a tone mapping with a color shift towards red or purple, given if we have a dusk or dawn condition. That's pretty much it. So it's very unrealistic. The same thing can be also seen in other models that we use. For example, we use a fog model, which is just blurring some of the parts of the image which are more far from the camera. And also we have a depth of field model, which is just a Gaussian blurring. So we have no distinction between foreground and background. I mean, it's very simple guidance in this case. That being said, we want to exploit these kind of models for guidance. So we have to understand one thing, which is that these models are highly unrealistic. So we don't want these models to actually influence the translation of the GAN. We just want to use them for the guidance. So in order to understand this, I'm going to give you a perspective of the formalism that is behind these assumptions, which is based, like the architecture is all based on this kind of formalism. So let's suppose that we have an image-to-image translation objective, which is mapping between a source and a target domain. And we call the source X and the target Y phi, while the phi represents the fact that we are interpreting the target domain in a continuous manner. For example, in the target, we have dawn, dusk, and night again. The idea is that suppose that if we have a perfect physical model, so a perfect physical understanding of the phenomenon which is behind the transformation, we don't even need an image-to-image translation network to perform our translation, because the physics is perfectly known, so we can directly map. In reality, what happens is that, as I shown you before, the models are highly unrealistic. So there is a discrepancy between the results that we can get with the physical model and the results that we can get with the generative adversarial network. What's important is that we have some real data, which is all mixed again, but the controllable, like the synthetic data, is instead very controllable, because in the physical model we are actually performing physical calculations which are indeed governed by our phi parameter. Again, we call our target domain in the physical model ym phi. So the idea is that given that we have this discrepancy between the two domains, we can identify different domain decompositions in order to distinguish between exclusive features of both domains and common ones. For exclusive features, I'm meaning something that appears only in one of the domains. For example, if we think about night, the fact that during night, the cars in a street scenario have their headlights turned on is something that is exclusive of a real domain because it's too difficult to model. And it's the same is valid for some model characteristics. So the idea is to disentangle the exclusive characteristics in the real domain and in the synthetic one, and to enforce that there is some kind of common characteristics, which is indeed continuous. So the fact that the common characteristics are evolving in a continuous manner means that we are able to control the real data, the real data transformation, even if we just learn this controllability from the synthetic data. So the idea, in other words, is that we should transmit the controllability of our physical model to the real domain generation. In any case, the domain decomposition is structured in this way. So we have for each of the target domains, the exclusive features and the common features. So since we have this domain formalism, what we did in the paper is to project this idea into the architectural level. So let's take a simple image-to-image translation system, which is typically composed by an encoder and a decoder. So we take an input image X, and we process them with a generic encoder to extract a hidden representation HX. At this point, what we do is to introduce our first architectural contribution, which is the disentanglement residual block, which actually projects what we have seen in the domain formalism. So the disentanglement residual block actually is just an application of 3 residual layers in parallel, which maps the hidden representation extracted by the encoder to all the atomic representation of exclusive features and common features that I've shown you before. So the idea of this is that we can now take this representation and recombine them in order to get some other hidden representation which are mapped to the target domains. So in this case, this hidden representation should be mapped to the target domain of the physical model, because it combines the hidden representation of exclusive features in M and the common ones. And the same can be done on the other branch for the real ones. Plus, we add some skip connection in order to improve the stability of the network. So in this case, what we are doing with the disentanglement residual block is disentangling by design some of the features of the exclusive features that the network is going to extract. This is the first requirement for our system to work. The second one is that the common characteristics are indeed controllable and evolving in a continuous manner. And this is not possible at the moment. So we want to control the path along our manifold with a phi parameter, which is not possible right now to inject in the image translation network. So the idea is that the residual layer, which is delegated to the extraction of the continuous common features, should have some kind of way to encode continuous information. And we do this by using one layer that we designed for the scope, which is called the functional instance normalization. So as regards the functional instance normalization, it's done to encode continuous information, and we take inspiration from the state-of-the-art related to style transfer, so in particular artistic style transfer. This is a perspective of the ADA-in layer, which is used for the scope of artistic style transfer. The idea is that we should be able to extract the style from a single image and apply that to an input image by just renormalizing the input features with an affine transformation parameter that are extracted from the style one. So it's very simple, it's very effective, but right now it's not suitable for continuous information, since we have just one set of parameter which is learned by extracting normalization statistics from one image. So the idea is that instead of having one single affine parameters, what we should have is a distribution of them. So we want to use a distribution of affine parameters in order to encode, let's say, to encode our transformation on a continuous manifold of a given shape. And we should be able to define that shape. So in this case, given that we have this shape, this continuous function that we call f gamma and f beta, depending if we are learning the gamma or beta parameters of the affine transformation, what we could do is, for example, assuming that we have the absolute positioning of images in our target manifold, so we assume to have supervision in this case, what we could do is to move along the learned manifold in order to renormalize and reorder the outputs. Of course, in the definition of functional instance normalization, there is this parameter f, which is a shape, that is the shape that we are using in order to define our target manifold. As I shown you before, we can have, for example, a linear encoding of our features if we want to perform a linear continuous image-to-image translation, or we can hypothesize also the cyclic one by using sinusoidal functions. This is very simple if we have this kind of supervision. So if we know which image is acquired at day, at night, at dawn, and we know the ordering of them, then the task is very easy. But in reality, what happens is that we don't have this kind of supervision. So in our setting, all the data, again, are mixed. So this is not sufficient in order to provide a continuous realistic transformation, and we need additional strategies. But it's a good way to encode the continuity inside the neural network, and we also think that it can be reused in other kind of applications. That being said, we are in the middle part of the architecture. So we have hidden representations that we may now map to their image in the target domains. For example, we can take the hidden representation in the synthetic physical model domain, and we can use a decoder in order to map it to a representation in the image domain. So in this case, what we are doing right now is simulating, reconstructing the output of the physical model M that we used with the same injected phi in the fin and in the physical model. So the idea is that this branch of the network, which is dedicated to the, let's say, physical model, should be able to reproduce the characteristics of the physical model that we are using for guidance. And for this reason, we use a reconstruction loss on the two images. On the other hand, we have a branch which should reconstruct realistic images. So what we do is taking the hidden representation associated to Y-phi and process them with the same decoder, and then train this branch of the network with a discriminator and a standard GAN loss. So we have, in this way, we have a meaning of the disentangled representation that we have, because this part of the network is going to encode characteristics which will be mapped to realistic features in the target domain, and this part of the network will encode instead characteristics will be mapped to the synthetic physical model. Right now, what we have is something which is controllable on this part, because we have a fee injection which is dependent here and here, but we don't have any reason why we should have a controllable generation of our realistic domain. So in this case, this doesn't work yet. So now I'm going to introduce you the most important architectural component in order to achieve the controllability of the output, which is the pairwise regression network, or FINET. So the idea of the FINET is that if we have a physical model, then it's completely controllable and we can output two different representations in the physical target domain with two different fees. So for example, for a single source image, we can get these two different representations in our target syntactic manifold. And we can also define the difference between phi and phi prime, which are the two phi that we are sampling randomly, as delta phi. At this point, we can get a neural network, in this case the FINET, which is trained to take as input a couple of images and output the phi difference. So in this case, what we can do is also taking the same phi that we used for the physical model generation and inject it in our disentanglement residual block in order to get a representation of the input image in the realistic domain for a given phi. So what we do in this case is to set additional constraints between the images that we have generated with the physical model and the images generated by the GAN. So in this case, for example, we can set a zero difference between these two images. This is very important because what the FINET is actually doing is mapping very different images on the same point on a learned manifold. So in other words, what is learning is a similarity criterion between the physical model and the real world. So at the end, this is the link between the unrealistic physical modeling and the real world. At the end, we can just train the FINET with all the constraints here that we have defined and a simple regression loss. So this is the complete architecture that I'm going to show you. We have the complete loss here, which is the composition of the adversarial loss of the discriminator, the reconstruction loss of the synthetic branch, and the FINET loss. So the idea, to sum this up and to get the takeaway, is that the discriminator is regulating the model realism, while the FINET is enforcing the network to encode continuity and to reorganize the translation by following the physical guidance. Of course, there are other architectural components that I'm not showing in terms of losses, for example, that they are used to improve stability. So if you want to look at that, you can discuss that later. The good thing about this is that also we can have a system which is model agnostic. So what we can do is taking some system which is state-of-the-art image-to-image translation and apply our system to that without any problem. So we can have actually a plugin to an image-to-image translation GAN. In this case, we take MUnit, which is a state-of-the-art network, and they get their continuous version CoMoMUnit, and the same we do for CycleGAN to a continuous CycleGAN CoMoCycleGAN, sorry. Anyways, I talked about the architecture, so let's talk maybe about the experiments, so we can also realign on the tasks that you are trying to achieve. Again, I'm going to talk mainly about the data time-lapse experiment, which is the most important one. We use the Waymo open dataset in order to perform the experiment. And we defined as a source domain, as I told you before, the daytime, while we have the mixed heterogeneous domain, which is dawn, dusk, and night. We use CoMoMUnit for the translation on a cyclic encoding to distinguish between dusk and dawn. So, first of all, qualitatively, you can see here a perspective on how the system works. So we have these middle images, which is the input of the GAN, while in the first circle, you can see all the possible translation along the learned manifold made by CoMoMUnit. So it's easy to see that the network is actually learning something which makes sense, because, for example, you can see that the night is the opposite condition as the day, and we pass from day to night in a smooth manner by passing towards intermediate conditions which are really difficult to learn, for example, the frontal sun or astronomical dusk, like these ones. And then if we pass from night to day, we pass through a realistic dawn setting, which is very different from the other branch, which is the dusk one. What we did also is to compare with the real data of the Waymo open dataset, in which we extracted the actual positioning on the learned manifold by using GPS data. So we actually used the sun elevation above or below the horizon in order to compare with our learned representation. So as you can see, the styles that we are actually learning, for example, this frontal sun representation, is actually coherent on what's happening with the real day. So what is exciting about this is that we have a high degree of physics controllability of the network. For example, we are able to say, let's generate images which have the sun at 0 degrees above the horizon, which is pretty cool. Of course, we didn't just evaluate this qualitatively. We also evaluate that as a regression task in terms of phi regression, so angle regression in this case, and we compare against different baselines which we outperform for a large margin by using an oracle, let's say. As regards baselines, I'm going to make you a little bit of a perspective of what are the baselines, because it's very complex to find actual baselines for this task, because continuous nonlinear image translation is new. So one of the baselines that we adapted is called DLOW, and it exploits the discriminator feedback to generate intermediate domains representation between a source and a target. Another one is the classical StarGAN B2. So the idea is that if we have a multi-target system like StarGAN, we can interpolate between the representation of different target domains, for example, dusk and night, in order to get a continuous translation. And finally, we have another baseline, which is called the deep network interpolation, which exploits the actual weight, so the actual kernel interpolation, in order to perform a continuous translation. So what is important about the baselines is that they are all way more supervised than ours. Because in order to get a continuous translation, so in order to get from day to dusk and dusk to night, all the baselines require additional supervision on what's dusk and dawn and what's night, because otherwise they are not able to reorganize automatically the target manifold. Instead, in CoMoGAN, we just used source and target annotations, so we are way less supervised. Also, we're able to work with cyclic manifolds, while baselines are just able to work with linear manifold. So with an intermediate condition, which is the mix of dawn and dusk. So I'm going to show you some qualitative results with this video. Again, this is a perspective on the driving scenes of the Waymo Open dataset. On the right, you can find the common unit outputs, and on the left, all the baselines that we have. So as you may notice, our translation is way smoother, and that's because our network is continuous by design. And we are able to get even better performances in terms of realism, also in terms of, for example, light appearance, stable night appearance, which means that our network is able both to increase the realism of the results and to increase the realism of the translation, of the continuous translation, so along all the manifold. So here I'm going to show you some additional results, for example, on urban scenarios, which are pretty coherent in terms of style, so they are pretty stable in terms of results, and they don't have artifacts. While it also generalized to this kind of suburban or highway also scenarios. That being said, about the qualitative evaluation, what we did is also to quantify this with some metric. For example, a very well-known and used metric for GAN realism is the inception distance, or FID. So what we could have done in this scenario is to just take all the images in the real domain and take our generated images between day and night, and then compare the feature distance on pre-trained networks on the ImageNet in order to get some kind of differences and quantify how our images differ in terms of feature activation between the activation of real data. What we did is also related to compare the translation quality in terms of continuity. So we had some additional insight about the evaluation. What we did is, instead of sampling images in all the target manifolds, so from day to night, we divided that into bins, and we evaluated the FID, so the activation distance for every bin in a rolling setting. So this leads us to this kind of plot, which is kind of complex to see, but it gives insightful results. So first of all, we can see that our curve, which is the blue one, is the best one in terms of mean FID. But it's very useful to see that they're in the rolling setting, so the blue plot here, we are performing way better than the other baselines when we are in the most difficult conditions to translate. For example, dawn, dusk, and night, which is the one where the network has to make more effort because they are more significant in terms of translation. So it's pretty cool that we are able to learn that the most difficult translation are the ones that are the most important ones in terms of quality. That being said, about the evaluation of the results, another cool thing about this is that we preserve the capabilities of the original network that we use as backbone. For example, Munit is a multimodal method, which means that for a given target domain, we can extract a different version of the same image in the target domain. So are we able to preserve the multimodality? The answer is yes, because if we move along our learned phi manifold, what we can do is to sample a given phi and to variate the style of the different images that are extracted in the target domain. So as you can see here, for example, this dusk scenario is way more colorful than the other ones. And in this middle style during night, we are able to encode differences between styles for a given thing. For example, here we have more lights. So we are able to preserve the capabilities of the original network. Okay, that being said, I will explain a little bit the other experiments. For example, this clear to foggy one. So in this experiment, we have a clear weather synthetic domain, which is Cynthia, and we want to translate into a realistic one, which is the composition of cityscapes, and a partially synthetic version of cityscapes, which is cityscapes foggy. That is the result of another work of our team. So the idea is to translate between synthetic to real and being able to regulate the fog intensity inside the generated image. Indeed, this is very interesting because even with no fog, we want to translate from synthetic to real. So we have a detached linear translation. Okay, here is a perspective of the qualitative evaluation. So we have source images and the guidance. So you can see that in CoMoUnit, even if we have no fog, we still perform the translation from synthetic to real, and we are able to move along the fog manifold in a realistic manner. What we did at this point of the research is to quantify if we are able to actually use this kind of images for data augmentation, for example, purposes. So what we did is to translate the whole Cynthia dataset and use this data for training segmentation networks. So what we did is training these segmentation networks and testing them on real data without fog, so on the set, and on real foggy images of the foggy driving dataset. So what we experienced is that we outperform greatly the other methods we are comparing with, but the interesting thing is that we outperform also MUnit, which is the backbone that we used for the CoMoMunit adaptation. And that's particularly interesting. I'm going to focus on this because MUnit is indeed, as I told you before, a multimodal method. So MUnit is actually able to represent different fog intensity. It's not like it's just outputting one fog intensity and we are way more effective because we have different fog intensities. No, MUnit is actually able to do this, but we are able to do that in an ordered manner. So why should this impact the segmentation performances so much? We try to give an explanation of this. So in this plot, you can see on the x-axis the fog intensity, and here are all the target data, like all the target data distributions. So we have images with no fog, images with slight fog, and so on. What MUnit is learning is to reproduce these styles in this manner. So it's actually able to reproduce the style that it sees, but it has no idea on what's between the styles. Instead, in CoMoMunit, what we have is interpolation by design. So we are able, in many parts of the translation, to actually have way more variability, on this part here, to actually improve the segmentation performances. And that was a cool part of the research process. We also had a final experiment on this DSLR effect approximation. So the idea is to take some iPhone capture images and to apply to them a depth of field effect typical of DSLR. And in this case, we compare with CycleGAN, which is a unimodal method. So CycleGAN is actually able to extract only this representation of the images. So this is the only style that we are getting, while we are able to vary the depth of field in order to get something which is also way more intense than the style extracted by CycleGAN. Okay, now that we have a perspective on what the system is doing, we also have analyzed the limitations and the possible developments. For example, asking ourselves, where can we go from here? One of the limitations, obviously, of the approach is that in inference stages, we are assuming our images to be in the, for example, the data to time lapse, we are assuming images to be in daytime, and we want to translate on other parts of the day. What we could hypothesize was, for example, to have an actually unknown position image inside of the manifold. For example, a nighttime image, but we don't know even it's nighttime. So we slightly modified the architecture with some estimation, the position estimation inside our target manifold, and we are able, in this case, to say, for example, okay, network, generate an image, and you may raise the sun in this image by 17.5 degrees. Or, for example, we are able to get an absolute output, for example, raise the sun in this image to -5 degrees below the horizon, or raise the sun to +30 degrees. So, of course, the quality of these images is lower because this kind of system also tends when they have to remove information, so from day to night, with respect to when they have to add information, so from night to day. And another thing that we investigated is related to another paper that came out recently, which is called Rethinking the Truly Unsupervised Image-to-Image Translation, or TUNIT. So in TUNIT, the authors argue that even a source and target distinction is supervision. So it's a supervision signal that should be avoided in a real scenario. So what they do is to combine a sort of clustering strategy in order to get some kind of domain inside a mixed set, like in our scenario, and to translate between these identified domains. So given that we have a mixed set of cats, they are able to extract a domain representation of the cats in an automatic manner, and they're able to translate any cat into any of these discovered domains. Of course, what Unity is not doing is identifying an ordering of the domain. So in this case, they are just identifying different breeds of cats. What we are doing instead is identifying an ordering, but we have the limitation that we have a source and target distinction. Well, the source and target distinction is motivated by the fact that our physical model for guidance exploits this distinction. For example, when we have the day to time-lapse model, assuming is that the input images belong to the day dataset. If we had instead an any-to-any model, which is able to map from any point to any point, then we may be able to get rid even of the source and target distinction and reorganize the target manifold automatically. So the experiments that we did are preliminary experiments on NISTEM, so on digits dataset. What we are able to do is hypothesize the existence of brightness models, for example, which is any-to-any, because it's just brightness normalization, or redness, for example. And we are able, given the single NISTEM dataset, so without source and target, to regulate the brightness and the redness without impacting the realism of the generated image. So again, this one is an extension capability of the network. Okay, that being said about CoMoGAN, so let's step back a little bit and instead talk about the other work, so the ECCV one, which instead exploits realistic models. So we are in a completely different setting. We don't have anymore any unrealistic model, but we want to actually perform a physics transformation on our target images. And this is called model-based occlusion disentanglement for image-to-image translation. So I'm going to restart from the beginning and make you see again the example that I've shown you before in an animated version. So again, here we have the clear weather to rainy transformation. And we can see again that even if the network is making some transformation that makes sense, for example, it's generating reflections here on the street, we have this kind of artifact which is really evident. And it's really ugly in terms of realism. I mean, a human being is actually able to extract immediately the information that these images are fake. We understood that this is related to the fact that the network is not able to distinguish between what's behind the lens and what's on the lens. So in this case, this artifact is a result of the occlusions that are on the lens, which for rainy scenarios are raindrops. So what the network is doing is extracting an entangled representation of the raindrops on the lens and what's behind the lens, associating so this representation to some element in the image. So as you can see, the trees here are associated to the raindrop representation. So they are generated with raindrops. Okay, so we actually stepped back a little bit and we asked ourselves, but we actually need an image-to-image translation network to render rain, because there are existing systems which are not based on GANs. Let's step back a little bit and talk about rain renderings. There is this previous works from our team that is used to render rainstreaks. So as you can see, in a completely physically based method, without any convolution neural network, we are able to augment the Kitty sequences, so acquired in clear weather, with this rain streak effect, which is kind of realistic. Also, there are other systems which approximate other characteristics of rainy scenes. For example, this ICRA works, which is able to render the raindrops on the lens from clear weather images. So several characteristics of rain are already modeled, so they're pretty realistic. But is that enough? Like, in a rainy setting, what we want also to see is the wetness that is on the ground. So there is some kind of missing piece of the puzzle. Are we able to extract a realistic model which is non-neural for wet scene generation? Well, maybe, but it's super difficult. Because for wet scene generation, we want to know the exact geometry of the scene, the exact reflectance of the scene. So it may not be sufficient to have a physics-only generation for rainy scenes. But we still want to benefit from the existing models, which are indeed realistic. So what we want to do is take, for example, from source clear weather images and process them with our physics-informed image-to-image translation GAN in order to get what we cannot render with the physical model. So in this case, the wetness. Once we have the wetness, what we can do is exploit the physical model existing in order to inject them inside the generated image in order to get our rainy target representation. So in this case, it's the composition between the contributions of the GAN and the contributions of the physical model, which is different from before, because before we just used the unrealistic model for guidance. Okay, this should be super easy if we had this kind of data. But we don't have data which is just wet, because in real life, what happens if we record data which are during rain, what happens is that the raindrops are impacting the camera. So what we have in the target domain is images which embed both representation, the wetness and the raindrops. So the idea is that we should be able to disentangle the wetness from the representation of the occlusions. And that's why we created this system. Also, an interesting thing about this is that physical models that we are using for image generation have some kind of parameters. For example, we are able to regulate the size, the shape, and the defocus blur of our rendered raindrops. What we can do in this case is also injecting different parameters inside the generated images, which is something that typically GANs cannot do. So the idea is that we can translate from clear weather to rainy, for example, with out of focus raindrops, as the one that I showed you before on the target images, or we can vary this parameter in order to get a completely different style, which is indeed, again, realistic. So we can really increase the variability of our generated output. Okay, at this point, how do we disentangle between the wetness and the raindrops, so the scene representation and the occlusion one? Well, we depart from the standard GAN training, in which we have a discriminator, which is trained to distinguish between real images here of the target domain and fake ones, so the ones generated by the generator, okay, which takes some input image as a clue for the structure of the scene. So the discriminator in this case is imposing that the generator generates the raindrops, because it's seeing the raindrops on the real images, so it's saying, okay, generator, please generate also this kind of feature inside the generated images. What we want to do in this case is to fool the discriminator with our physical model. So instead of directly submitting the images generated by the generator, what we are doing is injecting our occlusion model, in this case raindrops, before forwarding them to the discriminator. And this means that the discriminator is still seeing images with raindrops on that, but the generator is not anymore required to generate them. So it can concentrate its translation capabilities on the disentangled version, that is the wetness. Of course, in order for this to work, the occlusions that we are going to generate must be in the same style as the real ones that we have in the target dataset. And this, as I shown you before, is really difficult, because in the occlusion model, we have many parameters that may be modified, and so the appearance of raindrops is going to be entirely different. So if you don't inject the same style of raindrops, the discriminator is going to immediately spot us. What we want to do in this case is to design an optimization pipeline in order to learn the optimal parameters in order to get the exact representation of the raindrops or general occlusions in the target dataset. How do we do that? Basically, what we do is first training an image-to-image translation system in an entangled manner without any physical clues. So the idea is that we should bootstrap our knowledge about the target domain by using the discriminator training. So the discriminator in a normal image translation network has some kind of clues on what's realistic in terms of the target domain. So it has some idea on how a rainy scene is done. Then what we want to do is to minimize the difference between the source images and the target representation learned by discriminator by just modifying the occlusion model parameters. So the idea is to implement our occlusion model in a differentiable manner and to backpropagate the gradient in an adversarial attack fashion just through the parameters of the occlusion model. So in other ways, what we are doing is performing an adversarial attack, but constraining the modifications that we can do to the source image just on our occlusion model. And in this case, we get to a minimum, which is indeed the optimal representation for the occlusions in the target domain. In this case, we can use these parameters in order to render our occlusions in the previously presented strategy. So I'm going to show you a little bit the results on this. So we have some real image here, which is acquired in clear weather. This is a new scenes dataset, which has recently been presented. And this is the target domain that we want to approximate. So we have a rainy scene with wetness and raindrops, okay? With our system, we are able to represent the target style in a very realistic manner. So as you can see here, we have both the wetness and the raindrops, like these elements, which are indeed similar to the ones that we get in target because of our adversarial estimation strategy. Still, we are able to control the raindrops in a disentangled manner. So we can vary their appearance or position, or for example, we can render images with just wetness, so without occlusions, which are indeed unseen in the target dataset. Again, what we can do is to modify the parameters of our occlusion model in order to get other unseen scenarios, like this one, which resembles the dashcam, or again, we can enforce video consistency in order to move the raindrops in a separate manner from the scene. So with respect to the video I shown you before, here this one is way more realistic because of our perceived raindrop effect. And we know that raindrops are on a windshield, so they should move in a different manner than the rest of the scene. So given that we have explicit controllability of these raindrops, we can even modify them like we just coding without having any neural clues. Of course, now I talked about physical conditions and rain. In the paper, we have some other more experiments on different conditions and on different physical models. For example, we are able to learn colorization in a disentangled manner. So passing from this kind of image, which is in grayscale, to this kind of images, but by just learning with this kind of target style. So the idea is to disentangle the colorization from the generation of this dirt spot, which may hurt training. And we are also able to reproduce them in a realistic manner. That being said, that was the work. So I hope I have to have interested you, and so we have some more time for questions and answers. If you want, I'm here to answer.
Thank you, Fabio, for the great presentation. It was very interesting. I see the great potential of using this for autonomous driving. And one of the challenges, for example, is depth estimation at night or rainy day. With your approach, you can convert the night scene to the day scene. Also for domain adaptation, since you can generate many images with a continuous translation, that can be, you already use one of them for segmentation, right?
Yeah. In particular, yeah, the foggy one. We actually concentrated on the foggy one because it's one of the most it's one of the most important applications in terms of variability, because when we record adverse weather scenarios, for example, it's difficult to record every possible range of adverse weather that we have. For example, let's think also about rain. We didn't experiment on rain, but it's very difficult to collect data sets with different intensities of rain and also to reorganize them. So with CoMoGAN, for example, we are able to make a sense of these, all this transformation, interpolate between them. So we hypothesize that it's going to be impactful in terms of how the network, how the segmentation network later can learn.
11 maybe.
Okay.
Yes, my question is how you make sure it's not collapsing to one of these representation. For example, how you make sure to disentangle of the features. Did you add some constraint?
In terms of the representation that the network is learning?
Yes, this representation. You have this shared common feature between the physical model and the translation part with the images, but how you make sure to disentangle of these three features?
Okay, so the idea is that this is collapsing if you don't add the pairwise regression network.
Okay.
So you're right in saying that, because that's actually what happens. If we don't actually force the network to use the continuous features, then the network is simply not using that for real generation. So if we take the complete architecture with a finite as well, what we are seeing is that the representation associated to the real domain is using both representation in both exclusive and common features. Okay, and this is the same for the opposite side. So the idea is that in order to minimize the L-phi loss, then the network has to actually exploit the phi information, because in the real domain, the network must actually be able to generate images which are similar to the syntactic domain. Okay, so in this case, what's happening is that all these features are indeed continuous, so they cannot represent they're continuous and common, so they cannot represent differences in these images. So the differences are actually implicitly enforced to be in the exclusive ones. So this is actually what is differentiating our outputs.
I see. So, do we have more questions?
I have a question. So from what I understood, like your guidance is always encoded as an image that I assume is like the same shape as the other one. Like, would it be an option to encode the guidance as like another modality, as like, I don't know, maybe text or something else?
Oh,
Something not an image, basically.
Yeah, I see. There are also some works I think that does something like this, and I see a great potential of this. We work mainly with images because, of course, with physics, it's easy to understand also the role of images in this kind of approaches. But yeah, I see no problems that you can guide with text, and I think there are many works also multimodal guidance which can be exploited.
Okay, thanks.
Welcome.
I have a question regarding the last part. So I think you did two separate things. In one case, you were just changing the parameters of the, let's say, raindrops. And in the second case, you were also optimizing the parameters of the image generator, right?
Yeah.
And you could get different results with them, right?
Like you are talking about this part of the presentation, right?
Yes. So if you just did that, then you just added raindrops onto the image. So I didn't understand completely what comes when you do just this part and when you do the other one. Okay.
When you do this part, you get an optimal set of parameters in order to reproduce only the raindrops. Okay. So at the end, what you have if you just have this is this kind of images, which is indeed in clear weather, but they have raindrops on the lens. Okay. Then what we want to learn is the disentangled representation of the rest of the scene. So once we have learned the raindrops appearance, we want to learn the wetness. And in order to learn the wetness, we exploit this optimal set of parameters in the adversarial training routine, which is this one.
And at that point, you fix the parameters, the length parameters, or?
I fix the lens parameter, yeah.
Okay. Okay, so that's how basically you don't need to have just samples that only have raindrops on the camera, basically.
Exactly.
Okay, makes sense.
Yeah, thanks for the question, because yeah, I actually forgot to say that the parameters in this case are actually fixed, learned and fixed. So it's actually wrapping of the parameters. Yeah.
Yes, but also something else that you mentioned, which is from the way I see it, is that both of them can be correct, because even the one which has this kind of fog region on the image, so it can happen because sometimes there are fogs in the air and sometimes there are some blocking because of raindrops, right? So to me, both can be realistic cases.
Yeah, indeed. In fact, what I showed you is the video, because it's where the unrealism is more evident in this case. But indeed, the representation that the network is extracting can be realistic under some assumption. For example, there are some frames in which the raindrop is just doesn't care about the physics, so it's super long, and it doesn't make much sense. But for example, if we look at this setting, it can be also realistic in terms of the target domain that we are extracting. Still, what we are able to do is to inject raindrops even in the target style with some physics consistency. For example, we can have, I'm going to show you before, we can have some raindrops which has some understanding on how the lights of the scene are. For example, look at this raindrop. This is not generable by an image translation network, because it's not capturing the fine grain detail by the fact that here there is a tree, so this tree should be projected by this on this raindrop. And secondly, yeah, the big advantage is that the quality of the translation is augmenting if we do that in a disentangled manner. And also we are able to modify the parameters. But of course, making the generator concentrate on the disentangled translation focuses the translation on other characteristics. So we actually get even better results in terms of also of metrics and diversity and so on.
Makes sense. Thank you very much.
Thank you.
Perfect. So do you have more questions?
Yeah, I have one question.
Yes.
It's a great work. I really liked it. But for example, if you go to slide maybe 12, 13, where you had the time and the images when you generate. So what I observed was that even though when we change the time of the day, the model still renders the same shadows.
Yeah.
Like I don't see the shadow moving because when the sun goes from dusk to dawn. So is it because of the model the physics model that we are, because it's very simple, it just changes the brightness. And that's what.
No, right question. I mean, it's very interesting, this part, because it's something that is related to the model that we are using, not in terms of physical model, but in terms of GAN architecture. So what we have seen is that shadows are not impacting the discriminative capabilities. So given that we have the same structure of the shadows, or we differ from, like we modify the shadows, if we don't have any other clues on why the shadow should be disposed in some manner, then this is not impacting translation realism. And also, all the methods that I presented, so MUnit and CycleGAN, are cycle consistency based methods. So when you work with cycle consistency networks, so when you impose a reconstruction between the translated image and the original one, what you are doing is fixing the structure of the scene, which is indeed very convenient for some part of the translation. Like, for example, you don't want to modify the structure of the scene, you just want to perform an image-to-image translation, but they're also fixing the shadows on the ground. What is cool about this is that there is some work on this direction. So, for example, recently, a very different work, but which tackles also shadow moving, has been presented at ECCV. I have some slide here, if I'm not wrong, like this one. It's from the EFROS group in Berkeley as well. And so they exploit multiple temporal data in order to relight a city. So they have also some understanding on the geometry of the scene. What is cool about the system is that the shadow's appearance is related to the GAN and not on the method itself, which means that if we adapt CoMoGAN to a system which is designed in order to modify the shadows, then the shadows are going to change, of course, assuming that we have some physical clues that is valid for this kind of transformation.
I see. But in the current model, we don't have any cyclic loss, like reconstruction loss.
Yeah, it's omitted for simplicity, but we do have a cycle consistency. Okay. Also, we had to adapt the cycle consistency to be, because in one case we are mapping from a pointwise domain to a continuous one, and in the other branch, because we have two branches, we are mapping from night to day. So when we map from night to day, we have to reconstruct the map. So we use an additional network component that we call finite in order to reproduce the absolute positioning on the original manifold here. Because here we are working with unsupervised mixed data. So we actually want to know where to position the reconstruction.
Okay, and the cyclic model, the reconstruction one is a separate model.
Yeah, it's between the images highlighted in red. So okay. For the day to night branch is on these ones, and for the night to day branch is on these ones.
Okay. Cool. Thanks.
Thank you.
So we have more questions or not?
A great talk, Fabian. Thank you for this presentation. I have two small things. Since you are using generative models, so is there any way to assess the quality of generated images?
Yeah. Actually, what we do is quantifying the quality of the generated images also with the traditional GAN metrics. So we compared with the baseline. It's not actually the main goal, even if it's a consequence of our method, to increase this kind of metrics, because it's also like the main focus of CoMoGAN is the reorganization. If we work, for example, with multimodal methods, it may happen that we have the same performances in terms of quality of generated images, but the normal methods are not able to reorganize the data. Still, what we observed is that CoMoGAN raises the metric, for example, in terms of inception score and conditional inception score, practically, because of the increased quality, because of the fact that we are regularizing the manifold, but also because of the translation diversity. So both metrics, all GAN metrics actually are influenced by by also the translation diversity. And the other thing about the quality of the generated images is about the FID. So with the FID, with respect to our baselines, we are actually measuring the fact that our images are indeed more similar to the real ones for a given manifold point. So for a given nighttime condition and so on. This plot. Mm-hmm. So indeed, yes, the quantification of the quality of the images is done. Of course, with GANs, it's always a tricky question, because it's very difficult to evaluate how our images are qualitatively better than others.
A second question is regarding if we have in the images specular surfaces. So can we use your wet model, physical model, or occlusion model to get rid of those surfaces? Like it would be in that context, it would be an inverse problem as.
Can you repeat which work are you talking about?
If we have specular surfaces inside image, for example, if we have in medical domain, if we have laparoscopic images, so because of the reflection of the light, so from the tissue you get a lot of specular surfaces on the image. So in that, it would be a little, I mean, I think it would be an inverse problem in that case.
Probably yes. It depends on I think it depends on the data that you have. For example, if you want to, like you're talking about this setting, no?
Mm-hmm.
If you have, instead of an occlusion model, if you have a specular model, then you can actually use that if you have some other kind of transformation that occurs behind. So suppose that you have a transformation and you have a specular effect, which is a DID, which is regulated by physics, and some other stuff, for example, a normal domain shift that can be related simply to the fact that we are using two different data sets. You can actually use that. It depends on the physical knowledge that you have on the scene. If you're working with data that are in a restricted scenario, for example, in a laboratory where you actually control the materials that we are working with, then I see that feasible. In autonomous driving, it's extremely difficult to render this effect with physical model, for example, on reflectivity, because we are in an unstructured and unknown scenario. So we don't know actually the materials that we are looking at. We don't know the geometry of the scene, even if we can estimate that with some depth estimation. So we focus this main contribution on occlusions. We do have an extension, which is in submission, that indeed works with general layers. So with general physical models which are added into the network. So I see that feasible. It depends on the knowledge of the physics that you have on the transformation.
Okay, thanks.
You're welcome.
Any more questions? Okay, let me ask the last questions.
Okay.
So what is the extension of this work? Where this direction goes in the future, some future, how you want to extend this work?
You meant this one?
The CVPR paper, I mean.
Oh, okay, the CVPR paper. Well, a possible extension is regulating our continuous translation on different axes. For example, we know that there are some hybrid conditions which are very difficult to model. Let's say, for example, that we want to regulate both the time-lapse generation and the amount of adverse weather condition. For example, we want to make rainy night with different degrees of rain. So instead of moving towards a bidimensional manifold or single-dimensional one, we want to move on a plane which is a little bit more complex, since we want to model all of the intermediate points. So we can envisage a multiple guidance on this. So a guidance on a time-lapse model and a guidance, for example, on the adverse weather model, which is very difficult to do, since we won't probably have all the data that we need. We will probably have only nighttime images or adverse weather images, and we may have some images in rainy nighttime. So this is going to be an interesting direction for an extension of this.
Perfect. So thanks again for the great presentation.
Thanks to you for the invitation.